Good afternoon, everyone, and welcome to the Purdue ECS Student Chapter MoChA webinar series. My name is Preeti Mitra, and I serve as the president of the Purdue ECS Student Chapter. And thank you all for joining us today. And we are delighted to have you here at our MoChA webinar series. MoChA, Modeling, Characterization, and Analytics, is our platform to bring together the academy and industry perspectives in electrochemical energy systems. And we are really excited about today's session. Purdue ECS Student Chapter aims to promote collaboration and discussion in electrochemical and solid-state sciences at Purdue and beyond. Over the years, we have organized initiatives such as WISE, Women in Electrochemical Sciences and Engineering, MoChA, Modeling, Characterization, and Analytics in Electrochemical Energy Systems, seminars and webinars, poster symposia, and workshops. We are honored to receive the 2022 Outstanding ECS Chapter Award for advancing scientific exchange in electrochemical energy systems. And we aim to bridge research, innovation, and career pathways in energy storage and conversion. Before we begin, I would like to acknowledge our founding and lead faculty advisor, Professor Parthopi Mukherjee, and his mentorship continues to guide and inspire our initiatives. And today, it's my great pleasure to introduce our today's speaker, Dr. Daniel Juarez Robles, Senior Research Engineer in the Powertrain Engineering Division at Southwest Research Institute. Dr. Robles earned his PhD in Mechanical Engineering from Purdue University, and especially he is an Energy and Transport Sciences Laboratory alum, and his expertise is in advanced battery safety and performance research, particularly in energy storage systems and lithium-ion batteries. Please join me in welcoming Dr. Daniel Juarez Robles. Dr. Robles, we are truly delighted to have you with us here today at 2026 MoChA webinar with your insights.
Thank you.
And the floor is yours. You can share with us.
Okay. Thank you very much. And thank you for inviting me to the Purdue ECS chapter webinar series. The topic that I'm going to talk about today is about structural insights and the correlation with the performance characterization of lithium-ion batteries. Now, since this talk is oriented to students, I want to give you some background about me in just a couple of slides before we jump into the actual content. I'm actually one of the former ETSL student. I was the lab manager for Dr. Professor Mukherjee's lab from 2015 to 2019. Here is a picture of me in front of the Flex lab with some of my colleagues. And I wanted to include this picture because since you are a student and you are at the point where you need to decide what you're going to do with your career, basically that's an open door for multiple options. And I can give you a couple of examples. After I graduated, I met with some of the new ETSL members, plus some of the old ETSL members, and some of my colleagues and some of my friends in this picture. They went into different directions. We took the same courses. We took the same most of the same courses. We did similar experiments or topics during our thesis, but each of us choose a different path. I can give you a couple of examples. There are one of my friends, Mistry or Bayrak, who went for academia. One of them is in School of Mines. The other one is at Purdue University. Another friend of mine, which is Ankit, the one over here, and Palau, they went for national labs. And some people like Deepti, the third person here. I don't know, you can see my pointer person, and me, we went for something more in the middle, which is a research institute. I will explain later what it means to be in a research institute, but It was merely coincidence that all of us met again during one of the ECS meetings, the 252. So as you can see, just because you start at the same from the same group or even the same school, it doesn't mean you will end up in the same career. Uh, so moving forward, Professor Mukari was there uh, in both cases. I forgot to mention that. About some of my professional background, I have a bachelor and master in mechanical engineering. So I'm working in lithium-ion batteries. I'm working in different energy storage systems, but my background is in mechanical engineering. Your background may be slightly different. You may be in other fields, but still, I try to prepare the material in such way that you can apply or understand the things that we're doing and the relevance to your field. Then I also did a master degree in applied math. Then I did my PhD at Purdue University, the School of Mechanical Engineering. During that time, and this part I want to highlight it, there was some collaboration between Purdue University and the UL Research Institute, between Professor Mukari and Dr. Judy G. Bryan, which was, all of them are part of the ECS chapter, Purdue ECS chapter. And thanks to that collaboration, when I finished my PhD, I was able to get a position at the UL Research Institute as a research scientist. I worked there for 3 years. I was doing some testing on lithium-ion batteries and some abuse tests. And later I moved to Southwest, which is now my current company. And here I'm a research engineer. I'm still doing some cell life and characterization of batteries packs. And I'm also supporting some projects related to immersion cooling systems. So I've been from different topics, starting from fuel cells down to lithium-ion batteries and some redox flow batteries. Now the topic that I want to talk today is lithium-ion batteries, but at the end I have some slides related to other chemistries. We know that there are multiple different energy storage systems. Some of them are based on electrochemical processes, thermal, mechanical, or hydrogen related. Fuel cells is the best example for hydrogen related. From the electrochemical part, which is our main interest, lithium-ion batteries have predominated the last 20 or 30 years, from 1980 until the 2020. And recently they started moving forward to other chemistries. Some of them are sodium ion or sodium sulfur, lithium metal, or even testing other magnesium or other chemistries. Uh, Other people are going into a different direction. Instead of having solid electrodes, they're going into liquid electrodes or liquid electrolytes. In that, sorry, basically liquid electrodes in flow batteries. Those are for large applications. In this case, we're looking for a small scale application and also electric vehicles. Across all those different chemistries, lithium-ion batteries is the one that covers two different ranges. One is going into the small scale, and it can be scaled up to large scale, like from 1 kilowatt up to 1 megawatt. So powering a small device up to powering maybe some large truck. And also it covers two different areas. Either you want to have a lot of energy stored or you want to have a lot of power stored. And then we make a small difference between those two cases. You can have a device that stores energy, and you want to have more energy per unit or per volume uh, area or per volume. In that case, that energy is stored there, but you also need to take into account how fast you want to release it. The faster you release the energy is what you call power. So in some cases, like if you have an electric vehicle, you want to have more energy because you want to drive a longer distance. But if you have maybe an sports car, you want to have more power. You want to go from 0 to 100 in less than 2 or 3 seconds. You want to release all the energy stored in a faster way. And lithium-ion batteries are in the middle of all these different properties. Uh, large and small power, energy, high energy power, and high energy density. There are other Across all the different storage systems, we will focus only on the batteries. We know that there are more chemistries, but we will not cover all of them. Each of them requires just a single presentation, and even that is not, it may not be sufficient. So there are different cells. There are some cells that are called primary cells. You use it once and then you dispose it. Those are the typical AA or AAA batteries. You also have a secondary on rechargeable batteries, the ones that we will discuss today. Those are lithium-ion batteries that can be used and then you recharge it and then you use it again and so on. Obviously, the life will decay as you continue using it. There are also some reserve batteries, which are similar to the primary cells, except that the reaction is not happening immediately. Maybe you want to have a reaction in 10 years, 20 years, and some of those are related to aerospace applications where you want to have some equipment that will be traveling for a long distance and then you want to use the energy. So those are some of the reserve batteries. The talk will be about rechargeable batteries. Now, it doesn't matter which electrochemical cell you use, which chemistry you use, all the cells have the same components. They have anode, cathode, electrolyte, and a separator. Cathode is considered the positive electrode, anode is the negative electrode, and they have a different potential. And as you know, when you have two different potentials, the potential different, you can use it to produce some work. And that work is, in this case, electrical work. Now, the energy that is stored in cathode or anode cannot be released in an abrupt way. It needs some path or it needs some transport mechanism to move it, and in that case, we have the electrolyte. Electrolyte in the lithium-ion battery is a combination of a solvent and a salt. Both of them are mixed, and it's not a single salt, there are multiple salts. But this ionic liquid will help you to move the ions from cathode to anode during charging and from anode to cathode during discharging. And since we don't have a direct contact between cathode and anode because all the energy will be released instantly, then we introduce a separator. The most common material is a microporous material that keeps them, that avoids having a direct contact. One of the reasons why people started using lithium-ion batteries because they have, as I mentioned, high energy and power density. They have a higher voltage in comparison with the hydrogen systems. They have a long life and a storage life. That also depends on if you use an LFP cell or an NMC cell. The cell life and the storage life will change, but it's a long life compared with other systems. It has a reasonable cost. At the beginning, it was expensive, but as we started having more and more manufacturers, the price started going down. And the most important thing is they can be manufactured in different shapes and sizes. That's more about adaptability and rather than adaptability to the application that you have. If you have maybe a cell phone or a laptop and you want to change the size, you can also change the battery size and adapt it to that specific application. That also brings additional problems like standardization. You don't have all with the same size, and it's hard to test two cells that don't have the same dimension or they have something different. Now, just to give you an idea how lithium look like when you mine it, it looks like a salt. You need to purify it, and once that you purify, you can get a lithium sheet, something like this. That's a malleable metal, similar to lead, that you can bend it with your hands, but it's highly reactive. Even if you expose it to a small amount of water or oxygen, it will react and it will turn black. So the black thing that you can see here is the lithium oxide. And even a small amount of this lithium metal, if you put it in contact with water, it has an aggressive reaction. So here is an example. They put maybe a few grams of lithium metal in the water. It start reacting, and the temperature can raise up to 60 or 70 degrees Celsius degrees in a few seconds. And that was just a small amount. For that reason, instead of using lithium metal in the cell, at the beginning they started using only some cathodes with a limited amount of lithium. Now there are different chemistries in the market, and I will not go into the detail in all of them. I just want to show this plot from uh, the battery report from the Volta Foundation from 2023. They were predicting that by 2030 we will have all these chemistries in the market. Some of them are becoming a reality, like having a lithium sulfur battery or having a LMFP or sodium ion cells. You can, if you Google some of this chemistry, you can actually find some cells that are available for purchasing. They may not be at the state of art for that specific chemistry, but they are available. And some of the common chemistries are for anode graphite, and for cathode are the ones that are here, NMC, LCO, and LFP. But not that we're moving to other chemistries, then we need to start migrating all these chemistries to new combinations. Maybe they will not be the ones that you'll be testing. Maybe the LFP will have an equivalent version on the sodium ion, or why not? If you pay attention, we have been using lithium, sodium, which are elements, sorry, hydrogen, lithium, and sodium, which are elements from the 1A group on the periodic table. But you can continue with that trend. Maybe look at the sodium magnesium ion and other different ions. Obviously, they're becoming bigger, and it's harder to find materials that can deal with that or intercalate them. We are also looking into different electrolytes. Electrolytes are highly flammable, and then when the cell goes into a failure condition, the electrolyte catch fires, and then that creates all these incidents that are publicized in the media. Just because of that, they start introducing some solid state or some semi-solid state cells, and they are also available in the market. They may not be the best ones, but there are some of them in the market, and they are also changing the separator. Now, what are the cell architectures? And I will try to cover this all these materials. If I give you an example, if I say think about a AA battery, I think most of us will have an idea on what's the size and even the voltage. You will think, oh, it's a 1.5 volts battery. And you don't need to be an expert in electrochemistry or even an engineer. You know those things because you use these cells uh, almost daily. Maybe directly or indirectly, but you are using them. And they have a very standardized size. You can think about size AA and AAA. The notation that they use is AAA is a small version of AA, 4A is a small version of AAA, and they have some larger cells, which means there was an A version from these batteries. But when you look at the lithium-ion batteries, they use a different notation. I give you a couple of examples. Like 50, they are giving you the diameter and the length. And if you look at the prismatic cells, they will give you the width, length, and thickness. But this is just one of the cells. If I have a cell with different dimensions, that will also change the format. Now, what are some of the batteries that are battery formats that are available right now? We can start with the coin cells. Those are the ones that we use in the lab to test new chemistries. Why we use these cells? Because they're small and it allows you to test multiple things without wasting maybe sometimes resources. Some of these cells are not dangerous. If they fail or something happen with the cell, the worst thing that will happen is you will have some electrolyte leakage and you just need to dispose it in a sealable bag. These cells, you can recognize them by the nomenclature. Either, let's say, the CR 2016, they are giving you the diameter and the thickness. And there are a large family of coin cells in the market. If you look at the cylindrical cells, we're familiar or we started getting familiar with the 18650, 21700. Recently, they introduced the 4680 due to Tesla. And you can compare it with the size that you have here. The difference between the coin cell and the cylindrical cells is it requires more material to prepare them. And they also have some safety features. If the cell fails, then somehow you can prevent the failure. The cell can include either a current interrupt device that is a pressure-based device Triggered safety device triggered by pressure, a PTC, positive temperature coefficient, which is a material that increases resistance as the temperature increase. And some cells, they actually have a printed circuit board inside of this part of the cell. Now, this is the most standardized cells that you will find in the market. But still, you can find other formats that are not, they don't have data dimension. This is an example from one of the battery manufacturers where they have cells with connections that are different. They're in the same size, or they have connections on both ends. So it's hard to automatize the way that you test some of these cells because they don't have the same format. And we haven't talked about the large scale. At the large scale, we have prismatic cells, pouch cells, and recently they started having a hybrid version between the prismatic and the pouch cells called the blade cells. So the prismatic cells, they have a hard case, as you can see here. Those are really large batteries, something between zero point 0.4 grams up to 6 kilograms, maybe 12 pounds if you want to put it in English units. They can store more energy, and the advantage of some of these cells, or the reason why they choose this format, is because you can pack it in a better way. Cylindrical cells are maybe more safer, but when you want to prepare a pack or want to put a pack together, the curvature that has the cell leaves a lot of space in the middle that sometimes increase the volume size of your battery pack. When you have a prismatic cell or a pouch cell, um, those those formats allow you to play with the size, in this case the length, width, and the thickness, and also choose where you want to have your connection. So for the pouch cell, you can have connections on both ends. You can have it at different, if you look at the tabs, which are the terminals at the top, those are separated at different distances. Some of them, they have like a longer distance, like a longer tab, just to distinguish which terminal is positive, like this one, which terminal is positive and which terminal is negative. How big are these cells? You can have something as small as like a very tiny pouch cell, or you can have a very large pouch cell as maybe something on the size of an A4 or a A3 sheet. They can be quite large. Uh, but as you can see here, none of these sizes are standardized, and the tab orientation is not standardized. But still, you still need to characterize these systems. And obviously, if you have more energy stored and there is a failure, then these cells will have more. There is a likelihood that the cell release more energy, or they can go into some explosion or some deflagration. Now, how do we manufacture some of these cells? When you talk about coin cells, the way that you prepare it is quite simple. You have all the parts, you can get them in the appropriate store, and the only thing that you change in this type of cells is the quartz anode and quartz cathode. In this case, we were using lithium metal as anode, and we were using a different material called copper tin as cathode. You can have a conventional cell with graphite in anode, graphite here, and LFP here, and then you can test it. Why this format is convenient is because, as I already mentioned, if you are testing a new chemistry and you want to see how it performs, you just prepare a small amount of that material, then you cast it in your electrode, you punch it, and you put it in your coin cell, and it's ready to test. If it doesn't work, you can dispose it and prepare a new one. In some cases, you can maybe prepare to hundreds or thousands of these coin cells just to test a single chemistry. Now, this is just at I will say at the lab scale. At some point, once that you're sure about your chemistry, you will move to a bigger format. And these applications are quite standardized because they say the format of the cell is already standardized. Now, the electrode within the cell, you still need to prepare the electrode. The electrode processing is also standardized. I will say you need to have your powders that you need to put in the cell. You need to mix them. You need to you need to you need to have the dry mix, then the wet mix. When you introduce some solvent and some binder, the binder will glue all the particles together. Then you will cast it into the copper or aluminum foil. depending on which chemistry you have. Some of the new chemistries only require one of them. And once that you cast it, you need to dry it. When you dry it, this powder will stick to the foils, and then you can start like trimming or cutting the electrode to the right size and put it in the cell. Now, just to give you an idea how the processing looks like when you go from the small scale to the large scale, you will see that the process is the same. You mix the slurry, you will have this wet slurry here, then you will cast it, set the desired initial thickness. When you cool it, just because you are removing the solvent, the electrode will compact. And then after that, if you want to control even more the thickness, you will calendar or press the electrode, and at the end, you will just cut it based on the size that you want. Some of those solvents they have some healthy hazard. They are cancerogenous. So they started moving to some aqueous base, and in some cases to some dry mixing, but the process is the same. And just to show you how the process looks like when you go to a medium scale, I will play this video. I will stop it at some point. So here you can see the electrode. They're casting the cathode material. You can see that it's cathode because here is a aluminum foil. Then the next step will be drying it. Here, the electrode looks at the beginning it was shiny, which means it was wet. It still had the solvent. Here you can see that now it's more like a dull, and it's because they already dried. The addition is really good. You can see that they are bending the electrode and still it's not detaching it. This long line that you see here is where they dry the electrode. So the electrode is moving and it's drying, and they're controlling every single step. Just I think one of the areas where the ETSL group is an expert is how to control this morphology and use it to control the performance in the long end. So once that you have your electrode here, you can move it to the cell assembly, whatever is the format that you choose. Now there are different, as I mentioned, there are different cell formats, and one of them is the pouch cell. In the pouch cell, what you need to do is once that you process your electrode, you already cast it, you dry it. Now you need to start adding the tabs. These tabs will be the connection between the cell and the terminals and the external terminals. And then you need to prepare also the pouch. The pouch is just a simple bag. It could be either a nickel or aluminum covered with some protective layer because the electrolyte is, at least the liquid electrolyte, is highly corrosive. And then you can start forming the cell. Once that you cut the cell, you can put the electrodes inside of the cell and fill it with electrolyte. Um, there are different formats on the pouch cell. One approach is you cut the small electrodes and then you stack them. Here you can see the either the positive or the negative electrode, and in the middle you have the separator. Then you introduce the next one. In this case, one of the electrodes is double layer, and some of the electrodes at the end is just a single layer. A different approach is having a single separator along the whole cell. I can give you a quick example. Some of the one separator from one of these large cells can be as long as maybe 20 feet or 30 feet, just to give you an idea how long they are. And another approach is having a sort of a jelly roll where you have anode, cathode, and the separator together, and then you put them in this C-fold formation. Since the pouch cell don't have a protection, except the pouch cell, which can act like a sort of a way to release some of the energy when the cell fails. Sometimes they introduce a PCB or a printed circuit board, which is the one that is shown here, and you can see here in some of the cells the yellow part at the top. Let me give you an example on how one of the C-fold and the stack processing look like. Here you can see how they're winding the electrode. On the left, you have the separator, anode is coming from the top. There is a second layer of separator and a cathode. You need two layers of separator because at some point you need to wind it, and then it will go back to the other side. So you need to protect the other side also from direct contact between anode and cathode. In the other case, in this case, if they're doing the C-stack, you can see how they are introducing one electrode, and they move to the next one. And here they are just controlling the position of the separator. It's a single separator. And you have this mechanism that comes and plug the next place the next electrode. Once that they're done, they remove the jelly roll and they put it in the pouch. For the cylindrical cell, it's a similar process. You have the different jelly rolls. Sorry, you have the different electrodes, anode and cathode, and the separator, and then you assemble it around a metallic element that it has in that is set in the middle, and then you fill it with electrolyte, and then you close it. Now there are some challenges here, which is removing some of the gases from the cell because you are trying to fill something that is already compact. In this case, the jelly roll is compact, and you are trying to put an electrolyte inside. Obviously, there will be some bubbles that will be caught in between the electrodes and the separator, and you need to remove it before you actually close the cell. The design of the cell is also, it changes. Initially, they used to have maybe one tab at the top, one tab at the bottom. This tab is connected to the external terminal. The other one is spot welded here in the base of the cell. You can see the terminal. Recently, they started introducing some new designs where instead of having a single terminal, you have a multiple terminals. That's called they call it either tabless, which is actually the opposite. Here you have a multiple tabs connected to the terminal that goes outside. And T cells, what they're aiming is to reducing uh, some of the internal resistance of the cell. Now imagine if the cell fails. Sometimes they have this mandrel or a piece of, it looks like a small cylinder or a small tube in the middle that directs the gases outside of the cell. This cell also has it, but in the difference between these two is that in one of them the gases can come out directly from the jelly roll. In the second one, just because the tabs are bended into the jelly into the cell, as you can see here, then they will not allow the gases to escape. So that will increase the internal pressure if this kind of cell fails. So they are solving one problem, in this case reducing the resistance, but they are also introducing other issues. And here is an example of how the single cell, single cylindrical cell is produced. So you can see here the same process is they do the same process. They prepare the electrode, then they cut it to the right size, and at some point here they will start assembling the cell. You can see here the cathode, they got the separator in the middle and another in the other side. And then they protect all the rest of the jelly roll with either with some extra layer of separator, or they also add some plastic just to prevent some contact between the casing and the electrodes. Once that they have the cell ready, they will place it into the can. They will fill it with electrolyte. I will skip it a little bit just to. Here you see how they start welding. They introduce this mandrel. They weld the tabs. They put the safety bands at the top. These are the safety bands. Is the welding, and then they will fill it, and then they will do the formation test. And then you will have your cell ready to be closed. At some point, they will put them in vacuum. The vacuum will remove all the bubbles, and they will degas the cells. And you just put some plastic layer at the end, and you have your cell ready. And you need to start doing the formation test on all those cells. Finally, the prismatic cell, they have a similar process. I will not spend time on that slide. So there are the internal structure of the cell is slightly different. Here you have a jelly roll, but the jelly roll can be oriented in different ways. Here, the jelly roll is oriented vertically, which means the electrodes are vertical, There are some cases where the jelly roll is oriented horizontally, and in that case, in case that there is a failure, the gases will be disposed on the side rather than the top. When your electrode is oriented in this way, your connection has to be on the side and not at the top, which is the usual connection for this cell. Some of them, they have just a single jelly roll. The ones that have a double jelly roll, like the one that is shown here, they have the connection in the middle, and you need to weld or you need to connect both jelly rolls to the external terminal. They have some protections, like you can see this blue oval in the middle. That's a safety event. If the cell fails, that will relieve the pressure that is building up due to the gases form. And when you fill the cell with electrolyte, it's filled through this hole that you can see here. Now, once again, just to show it in a video, here you can see the full process. They prepare the jelly roll where they press it just to reduce the space from the electrode. Then in the next step, they start adding the terminals. The terminals start in the middle. Here you can see the double jelly rolling. Let me go back a little bit. Here you can see one of the cells. You can see the double jelly roll here and how was connected in one of the sides. Then the next step will be to cover the both jelly rolls with another protection. So here they already cover both layers, and now it looks like a single element. And then they'll put it in the cell can. They need to weld the once that they put it in the cell, they need to weld. They need to solder the edge and make sure that there are no holes and there is no leakage. And then you will have you need to fill the cell with electrolyte at the top. Now, I already mentioned that the format influences the way that you characterize cells. In which sense? One is connections. If you have standard sizes, that's very simple. You just use one of the holders that is in the market, you plug it, you run your test. If you are using a new cell with a new format, then you need to customize your cell holder. And when you customize your cell holder, you are introducing resistances that are not considered initially in the connections. You also need to consider the thermal and electrical characterization. If you go from a coin cell to a large prismatic cell, in one of them your thermal mass is very low. So you will not see a significant thermal gradient. But if you go to some pouch cell and you are applying a large current, you will see a temperature spike at some point. So in one of them, we may see 1 or 2 degrees temperature change. In the other one, you will see maybe 20 or 30 degrees. And just because you are changing your temperature, your properties of the cell properties are changing and the performance will also be changing. And you also need to consider that in the battery pack. It's not the same to assemble a cylindrical cell or a pouch. You also need to consider if you're looking at the state of health, sometimes you look at the Coulombic efficiency or the capacity, uh, but that capacity is defined by the cell resistance. If you have a higher resistance, then you may get a lower capacity. But if you are introducing additional factors just because your cell is different or your connections are different, then that will also affect the results that you get and the way that you interpret your results. Also, from the safety point of view, let's say you want to make sure that when you standardize the test, especially for standard testing, you need to make sure that the conditions that you set are the same for a small scale to a large scale, and they are representative for all the different chemistries, which is already a challenge. So one example that I want to give is let's say you have one of the prismatic cell and you need to drive it into thermal runaway. You need to first decide where you place your heater. Will you place it at the bottom? Will you place it at the top? If you don't know anything about the cell, you may end up placing it in a location where the cell may not go into thermal runaway. You think the cell is safe just because nothing happened, but maybe that position was not representative from where the cell could fail in a real condition. So knowing about the cell format or knowing have a priori information on the internal structure is quite helpful, especially for safety tests. And also, when the cell fails, sometimes the case rupture. Sometimes when the cell goes into thermal runaway, even if it's a prismatic cell, you can see some rupture on the casing, and you think, oh, maybe it's because this happened or that happened. But it could be just the way that you oriented your or the way that the jelly roll has the electrodes oriented. Maybe that will change the weight or the thermal gradient, and that will produce a different response that if you change the orientation of the electrode. Obviously, you cannot change some of those things. That's more on the from the industry point of view, but those are some of the things that you need to consider uh, during during the manufacturing, and also the way that you instrument your cell. If you want to capture a true cell temperature, you need to know what's the best location based on each of the formats. Now, what I talk about here is formats for lithium-ion batteries, but that can be extended to other chemistries. You talk about solid-state batteries or semi-solid-state batteries. You can find some of these cells uh, in the pouch cell format, uh, and then you will face the same issues. In some of these batteries, if you are interested on testing them, there are plenty of areas that you can test, and I'm talking from the academia point of view. You can be interested from the electrochemical point of view. You can maybe work on the materials being in the lab and testing new chemistries, or you can be interested on designing the cell format or changing the materials uh, of the electrolyte, in this case, the solid electrolyte. You could be working on the chemistry, trying to come out with new salts or solvents or additives for the electrolyte, or from the thermofluid point of view, maybe you want to know how to dry the electrode or how to fill the electrolyte. In the case of the in the case of the liquid electrolyte cells, or in the case of the solid state batteries, how to basically immerse some of the cathode into the electrolyte. You may need to know some of these areas, or you can be part of that by working in some of these areas. Similarly, if you are interested in new chemistries, maybe you think, oh, we already know everything about lithium-ion batteries. Maybe we can test some sodium-ion batteries. You will need to face some of those issues that I mentioned. You will need to deal with the form factor. You will need to deal with the internal structure. And at the end, the cell response will be a combination of all these factors. And you cannot be limited to only sodium ion. You can test other battery technologies like magnesium ion, which are still they're not in a mature state, but they're still in the market. And there are more areas of opportunities, at least for the students that are in the code, where you may not be interested in the chemical part or the chemistry part, but you can be interested in the thermal issues, how to control the temperature so the cell doesn't go into thermal runaway, or to control it so it can have a longer performance. And by just playing with the cell format or playing with the way that you put your cooling system, you can control that. If you are more interested in the modeling or coding, you can work on the battery system in the BMS or the software, or find a way to estimate the state of charge or the state of health based on data, or based on experimental data, or based on a physical model, or why not introduce some of the artificial intelligence just to trying to predict what will be the cell life by having some initial information from the cell. So there are multiple areas uh, the new where you can still jump into the battery field, not only lithium-ion batteries, but all the different uh, chemistries. And just to stay in time, I want to talk about the company where I work and the things that, how we address some of these issues. So the company where am I is a Software Research Institute. We're located in San Antonio. Our office is here, but everything you see here in this area are our testing facilities. And we can test from batteries, small batteries to large battery packs. We have some facilities here. We can test maybe an electric vehicle pack, and then do some performance testing on some safety testing. In the area of lithium-ion batteries, we can test everything from environmental testing, mechanical testing, like a nail penetration or crushing. If you have an electric vehicle, we can characterize the cell vehicle or some of the parts from the vehicle. We can extract some of the cells from the vehicle and also evaluate at a specific sample. We can analyze the thermal, can do some thermal analysis from the experimental point of view and also from the modeling point of view. We can do some immersion cooling system, performance and abuse, and we can also test material for the batteries. Where we are in terms of the technology spectrum. So there are two, and I'm talking about the once again for the student. When you finish your undergrad or your grad studies, you will have multiple options whether you go to industry or you go to some university or national labs. In some of them, will be working more on fundamental sciences, like you are a professor or a researcher in a national lab. And if you go to the industry, you'll be working more with some specific products on some specific, basically in the product development all the time. What we do here is something in the middle. We try to connect some of the basic research and apply it to some of the industry requirements. And sometimes we're doing more work on one side or more work on the other side. I will say we're maybe 30 to 70, 20% more oriented to industry, 30% more on universities. And then we can, it's not about only developing one product for industry, it's more about showing them how the product will behave under certain conditions. And by product, I mean lithium ion, sodium ion, or whatever is the chemistry do you want to test. And when you want to test all these things, what I show you in the previous slides is there is a very wide spectrum of what will be the cell. So one day, one manufacturer can come and say, I want to test this cell with this weird format, with this weird chemistry, but I still want to test it. I want to know something. And you still need to have the capabilities to do it. Now, if you're interested in being part of or learn how we perform some of these tasks, we have some available summer research internship every year. You can apply. I think it's directed for undergrads and some grad students or master students. But you can, if you're interested, you can shoot me an email and you can come here. You will get some stipend and also work in actual projects. It's not about just sitting there and looking for papers or things like that. It's more a hands-on summer internship. And just to, I will take 3 or 4 more minutes just to show one example. So recently, I don't know if you notice it, but at least the students started working with batteries. And there is a recent trend where the cell started becoming larger and larger. And what happens when the cell becomes larger is you put more energy in the cell because that's what you want. You are putting more capacity. Your mass is going up, but what is happening also is the resistance is going down. Now, if you want to characterize this cell, when you want to connect some of these large batteries into some battery cycler, it happens that the resistance of your battery is in the same order as the cables. So now your cables that you are connecting, they have the same resistance as your cell. And what happens is you will have some confounding effect of both cases. And now when you need to develop like a new methods to test some of those large batteries. And just to give you one more, this is just a general example. There are I did a small survey online, and you can find very easily some cells like some electric cells. This is a cylindrical cell, 50 ampere hour. If you're familiar with the cell, you'll note that a cylindrical cell, especially the 18650, they don't go above 3 or 4 ampere hours. These are 50 ampere hours. And you want to test it, and those are like a 1.1 kilograms. Resistance is 0.7 millions. When you compare it with the 18650, 18650 is in the 40 millions. This is 1 over 40 less than the other cell, so it's very small resistance. If you want to test something even larger, let's say you have this one of these blade cells, these are 400 ampere hours. What happens if you have 400 ampere hours and the rate that you want to test is 1C? That means you need to have a system that can deliver 400 amps, right? Uh, and sometimes you don't want to test only 1C, you want to test 3C. So you need to go to maybe 1200 amps. So you need to have a system capable for that, and you need to make sure that everything is capable of testing it. Now look at this, the size of this cell. This is 960 millimeters. This cell is almost 1 meter long. So do you have a thermal chamber where you can feed some of these cells? Do you have a cycler where you can accommodate this system? So those are some of the challenges that happen once that you move from the lab scale to the actual to the industry scale. They want to go bigger. They still want to test. And so those are some of the things that we do. And in another example is this 472 ampere hour cell. This is 8 kilograms. And once again, you need to apply a very large current, and the resistance is quite large. So your connections are not good. You will be influencing in the way that the cell will respond. We have all the requirements to test that. To start with, we test all the different standards, UN, UL, EAC, and we go from the cell level up to the battery level. And we have all the requirements to test not only cell-to-cell variation, also characterize them, like get the capacity, get the charge and discharge resistance and efficiency, and test it on the real conditions, not only CCCV charge and CC discharge, but also applying some dry cycles into some of these large cells. And also do some safety evaluation from single cell to a large battery pack. And obviously, as some of the industries interested, they want to make sure that the cells are safer to put them in the market. So we can test either from a single cell, which is something that we can do at the lab scale, but also in some battery packs. And we have the capability to control, to measure the gases, and also collect them and dispose them in a safer way. And with that, I will conclude the presentation.
Thank you so much, Dr. Robles, for the insightful and engaging presentation. And we truly appreciate you sharing your expertise and experiences with us, especially as an ETSL alum venturing to our community. At this point, I would like to hand over this to our Vice President, Pooja Ranganathan, who will moderate the Q&A session. Pooja, the floor is yours.
Okay, thank you, Pretty. Daniel, thank you so much for this very engaging talk. Actually, it was almost like a shadowing internship that we went through each stage of cell manufacturing and assembly line. It was very insightful. Thank you. And actually, I personally work on sodium ion batteries. I work more on characterizing interface and understanding how it's responsible, like either cathode electrolyte interface or solid electrolyte interface. And I try and understand how that particularly affects thermoelectrochemical instabilities in sodium batteries. So, I mean, after listening to everything that you talked about, the first question that comes to my mind right now is like in an academic lab setting, how do we at least take steps, or like what are the measures you think is kind of helpful in bridging the gap between what we do in a university lab, and how can we revise our protocols more in the sense that it might be more useful to a real world application?
Yeah, this is a really good question. So you're working a very small scale, still working
Uh-huh.
with coin cells. The
Yes.
best thing that you can do is one, be very careful when you prepare the coin cells. Make sure that you can repeat every single step, even just putting the electrolyte inside, and
Yes.
make sure your connections are the best. And something that we found is
Mm-hmm.
when you are introducing additional factors like resistance, and
Mm-hmm.
for coin cell resistance is quite high,
Mm-hmm.
then sometimes that doesn't let you see the true performance of the material. You will need to go to a very low C rates and so on. But as
Mm-hmm.
long as you can control connections and you can control temperature,
Mm-hmm.
you will get more consistent results.
Mm-hmm.
I have one example when I was at the ETSL lab. We have
Mm-hmm.
a battery cycler, and it was next to the lab door. So every time that they open the door,
Uh-huh.
uh, every time that somebody opened the door, they were changing the cell temperature. And at
Oh.
some point, we noticed that during the night, we have very consistent results, and during
Mm.
the day, the results were like we had some spike on a spike. And it was
Yes.
nothing else that we didn't insulate our system, or at least our 18650 cells enough. We didn't cover it, or and then we have some influence from other factors. Obviously,
Mm-hmm.
you will take care of all the preparation and the electro processing, but you also
Mm-hmm.
need to consider the external factors. And sometimes we don't consider that. We think, oh, coincide is ready, plug it, run, and let's go. No, it's pay more
Yeah.
attention to the test conditions, I would say.
Yeah, actually, yeah. Like, so for sodium ion batteries in our lab right now, we code the electrodes manually as well. So I have actually seen the difference between the capacity during summers and when I code it during the winters, that
Yeah,
again influences the capacity value. So it's like a cycle of repetitions and yeah, multiple experiments. So yeah,
yeah.
thank you for that, guys. I mean, since I had the question right away in mind, I just asked you, students, like if you have any questions about the talk, I would request you to like put it in the chat box, please. Yeah, anyone have any questions, you can type it in the chat box. Okay, actually, yeah, I mean, if meanwhile when they're typing, I just had one more question, please. So, I mean, as an experimental researcher, we as grad students like go on testing, experimenting, characterizing with just a limited perspective of, academic lab scale setting, right? I would like to know from you, like when you're interviewing a fresh PhD graduate, what are the skills that you look for at this stage? So, I mean, I'm sure as a student, you have a very different perspective on how research works. So, but when you go out, you might need a different mindset. And I would like to know from you what you look for.
Uh, so usually, based on the type of test that we're doing, we're looking for innovative thinking. Not innovative in the sense that we will come with a new chemistry out of
Yeah.
our out of the blue, but more
Mm-hmm.
on the if I give you something that you haven't tested before, how will
Mm-hmm.
you approach it? Let's say I remember one of the questions from one of the interview was you have a you have a internal combustion engine car and you
Mm-hmm.
want to convert it to some electric vehicle, what will you do?
Wow. Okay.
It's not like you have a full solution to the problem, but what we're looking is how will
Mm.
you approach to that problem? And that's
Got it.
something that we're looking for in some of the people because it's we're not dealing with the same test all the time, and sometimes you need to come out. You need to use everything you know.
Mm-hmm.
Even if you're experimentalist, you still need to take courses of thermodynamics, fluid
Mm-hmm.
dynamics, math, or at least do some basic modeling. And I will not say modeling to solving PDEs or ODEs, but
Mm-hmm.
still you need to do some basic data analysis.
Mm-hmm.
So if I say, okay, if I have this data on this cell and I want to predict the cell life,
Mm-hmm.
you should be able to give me an answer. Is it a good answer or
Yes.
not? But you still should be able to come out with some procedure. You say,
Got
okay, I'll do some curve fitting. Maybe that's the quickest solution if you want to get an answer today. But if you
Mm,
want to get something more accurate, then you will introduce some physics based.
mm.
So those are the things that I will look for in some new employees, that they have that they can think out of the box and that they can use everything they know. They may not be the experts on lithium-ion batteries, but at least they know what they will do or how they approach it or who will they approach, even knowing some people that also helpful.
Thank you. Thank you so much.
Yeah.
Yeah. So on that note, like, how did you, when you were a grad student, prepare for your applications? Like, did you know a few places that you wanted to go already, or like, did your path, like, did your mindset change from the beginning, like towards the end of PhD? So how was it for you?
It was so I would say for me it was uh a special case, and I'll tell you why. Because I was already in contact with the industry before I started.
Oh, okay. Okay.
So I knew some people in the industry, and it was just because we were always in conferences presenting material, and in
Mm-hmm.
those conferences we met some of the not some people from other universities, but also people from industry, and they knew what what I was doing.
Okay.
So part of the collaboration that we did with UL helped me to get that position when I finished.
Mm.
Uh, and then at some point I decided to I had to move to another company, and yeah, at that point I have a different, we'll say, I was in a different, I already experienced how the industry works and what I was expecting from a different position. So I was
Mm.
more careful about the places or the companies where I applied because I knew what I wanted. I wanted to test real things. That was something important for me. So whenever I applied to different companies, I was looking for that. For me, professional satisfaction was very important. I wanted to be in a place where if I spend 20 hours working or 10 hours working, 20 hours is an exaggeration, but if I spend 10 hours working, that I enjoy those 10 hours. I don't want to be in a
Definitely.
place where I maybe work 7 hours or 6 hours, but I don't like what I do. So that
Yeah.
part was important for me. And that's something that you need to consider when you
Mm.
choose certain career. And don't stay in like something that happened in the industry, at least
Mm.
the battery industry is people is always moving.
Mm.
Maybe at the beginning you will get a position in some company, but that may not fulfill either your financial or professional or personal
Mhm.
requirement. You know that at some point you can move to a different company. You already gained some experience. Just bring that experience to the next company. And some people do that. They work for 3 or 4 years in one company, then they move to another one, and they move to another one. Since they're gaining experience, they're also improving at least the economical part and also the position that they get. Yeah.
Yeah, makes sense. So, yeah, that there just a follow up on this actually. So I see you like what you're doing right now. So would you consider changing your field of, I mean, would you consider actually getting into industry or academia at this point of time?
Not really. I already spent some time in academia.
Mm-hmm.
Uh, I was a lecturer in my university for 3 or 4 years, and I was
Mm-hmm.
also a lecturer in high school for 10 years. So I already experienced the academia part, and I wanted to test something more real, but that was relevant for me. That doesn't mean it has to be the case for you. Some of you may be interested more on still bringing more knowledge and science, and in that case, academia and uh, national laws are perfect for you. You will get everything that you need, resources, material, uh, but it depends. It depends what everybody wants. As
Yes.
long as you have clear what you want,
Mm.
that should be an easy decision.
Okay. Okay. Yeah, perfect. Thank you. Thank you so much for that. Uh,
And
yeah.
and we truly appreciate your time. giving us to share your expertise with us. And before we conclude, we would love to take a quick group photo all together. So please feel free to uh, turn on your cameras if you're comfortable. Then we'd like to take a picture. Yeah.
Cheats.
Yeah. Did you take one? Yeah.
Thank you so much. Sharing your insights with us, and have a wonderful day. And will share if after getting the approval of recording to our YouTube channel. So keep stay tuned with us. Thank you so much, Dr. Robles. Have a nice day.
Thank you.
Thank you for your time, Dr. Robles. It was such a pleasure having you. Thank you so much.
Thank you so much, everyone.
Thank you. Bye.
Bye bye. Yeah.